Today we're going to talk about finding the rules of exponents. The first rule is when you add the powers. Now, a problem that has adding powers looks like this. 2a to the 5th times 3a to the 7th. If you take a look at this problem, only the a's actually have an exponent attached to them. So we're going to put parentheses around those so we can separate them. Whenever you see multiplication between two sets of powers or sets of powers and their coefficient, which is what we have here, you're going to add the powers. So if I just deal with my exponents, I've got a to the 5th and a to the 7th. So it turns into a to the 5 plus 7. And a to the 5 plus 7 is a to the 12th. So I add the powers. However, the value in front of the a, the 2 and the 3, are actually called coefficients. Whenever you have coefficients, you still follow whatever operation is between them. There's multiplication between these two values, so you're going to multiply 2 times 3, and your answer is 6a to the 12th. The second rule is when you're raising a power to a power. We're going to see two different examples of this one. In the first example, we are going to use the variable m squared, and we are going to raise it to the 4th power. Now, whenever you do m squared to the 4th power, it's really saying m squared times m squared times m squared times m squared. So you write that out 4 times. If you apply your adding powers rule, it's multiplication between these 4 values. So you're just adding 2 4 times. 2 plus 2 plus 2 plus 2 is 8. So it is m to the 8th. The shortcut rule is just multiply the powers. You're only raising a power to a power when the power is outside of the parentheses. Now, if there's a coefficient inside your parenthesis with the power, for example, 2n to the 3rd, and then we're going to raise that one to the 3rd power. That power outside the parenthesis is distributed to both values inside the parenthesis. Now it's clear that the second value, n to the 3rd, has a power, but I don't see a power on the 2 right now. There's always an imaginary 1 power, so this is really 2 to the 1st. Now that we know that's 2 to the 1st, we're going to multiply both sets of powers. So 2 to the 1st, I'm going to multiply times 3, so that becomes 2 to the 3rd. I'm also going to multiply the other 2 powers. 3 times 3 is 9, so this becomes 2 to the 3rd, n to the 9th, and we know 2 to the 3rd is 8, so we are going to write our answer as 8n to the 9th. The next rule is subtracting powers. You subtract powers whenever there's division. Now it's important that you can only subtract the powers if they have the same base. If there's different bases, you can't subtract them. We're going to see 3 different examples, one with just a variable, one with 2 variables, and then one with some coefficients. So if you take a look at my first example, we're going to use y to the 7th over y squared. Now there's division between these 2 powers right here, so we are going to subtract them. Y to the 7th minus y squared just turns into the y to the 5th. If you want to know why we subtract them, you would write out y to the 7th as just y 7 times. So if you look down here, there's y written 7 times. On the bottom, we've got y written 2 times. Okay? Well, remember that whenever you have the same value in the top and bottom, they cancel. So I've got a y in the top and bottom. I'm going to cross them out. I've got a y in the top and bottom. I'm going to cross them out. I'm left with 5 y's. So my answer is y to the 5th. My second example is going to have 2 variables. I'm going to have x to the 4th z squared over x squared z. Now I'm going to keep these positive powers for the moment because we haven't reviewed negative powers in this video. I have 2 different powers with 2 different bases. I'm going to subtract the common bases, so I can subtract the x's and I can subtract the z's. Now it's always a good idea whenever you have a problem like this to draw a line in between all your separate values so you can see the 2 powers. So if I take care of the first part, x to the 4th minus x squared just becomes x squared. Since the 4 is in the top, I'm going to leave my answer in the top. It's x to the positive second power. Remember that there's an imaginary 1 on top of this z right here, so this is really z to the first power. 2 minus 1 is just 1, so this becomes z to the first, which you could rewrite as just x squared z. The last example is going to have a coefficient in it. We are going to do 2m to the fifth over 4m squared. Now, whenever you have a coefficient, which means just a number in front of the variable, when you separate them out, you have to treat this like normal division. So if we take care of our powers first, m to the fifth over m squared reduces to m to the third. Now we've got 2 divided by 4. Well, 2 divided by 4 gives me a decimal, and we don't usually write our answer with exponents in decimals. So I'm going to treat this as a fraction. This is really the fraction 2 over 4. I know the fraction 2 over 4 simplifies to 1/2. So when I write my answer, I'm going to write 1/2 m to the third. Now, I can either leave 1 m to the third in the top and just put a 2 underneath it, which is the same answer if I just wrote my answer as m to the third over 2. I do not have to put that 1 in the numerator as long as there is something else in the numerator. Now, if that m to the third wasn't there, you leave it as 1/2. But since the m to the third is there, you can rewrite it without the 1 in the numerator. The next one is finding powers of products and quotients. Now, the first thing that you want to do is remember to distribute that power to everything inside of the parentheses. So if you take a look at this first example right here, 1/3 x squared to the third power. Okay, I have three different values, inside my parentheses, so I'm going to distribute this to every single one of them. I still have to follow normal exponent rules. So once I distribute the power, then I would simplify my answer if I need to, using any of these 3 methods over on the other side. So if I distribute this, this turns into 1 to the third, x to the 6th, because remember, I'm raising a power to a power, so I multiply the 2 values, and then 3 to the third. Now, I can't leave my answer like this, so I'm going to, because I can't have the exponents on my numbers, so I'm going to come over to the side. 1 to the third is just 1. I can't simplify x to the 6th because I don't know what x equals, and 3 to the third is 27, so my answer is 1x over 6 over 27. Remembering that I don't have to leave that 1 in the numerator, I can also write my answer as x to the 6th over 27. Now, if I had a similar example like this, where I had m to the 4th over m squared raised to the 5th power, I can do one of 2 things. I can either simplify inside my parentheses first, then raise it to a power, and I can do that because I have the same base, or I can raise both of these to the power of 5 and then simplify. Either way, you're going to get the same answer. So if I start the first way, I'm going to simplify inside the parentheses, m to the 4th over m squared. I subtract the powers, so that becomes m squared to the 5th power, which is just m to the 10th because you multiply the powers. If I wanted to simplify before I started, I would do m to the 20th over m to the 10th because I distribute that 5 to both values. If I simplify this using my subtraction rule, 20 minus 10 is 10, so my answer stays m to the 10th. It doesn't matter which way you simplify as long as you are consistent throughout your problem.